Anyone who has watched Matthew McConaughey plunge into a supermassive black hole in Interstellar might feel as though they already understand what it would be like to encounter one of these immense, terrifying cosmic monsters. The movie's gripping visuals, emotional stakes, and scientifically inspired sequences give viewers a dramatic sense of the unknown. But even the most brilliantly crafted Hollywood blockbuster, set decades in the future and guided by the meticulous attention of director Christopher Nolan, can only offer a highly stylized interpretation. The reality of a black hole, its immense gravitational pull, its distortion of space and time, and the unimaginable fate that awaits anything that ventures too close, is far stranger and more extreme than fiction can convey. Now, 10 years after Interstellar first arrived in theaters, NASA is offering something even more remarkable, a far more personal, scientifically grounded, and detailed simulation that imagines exactly what a human would see and experience while falling toward the event horizon of a supermassive black hole. Of course, no human being has ever come close to one of these cosmic giants. The nearest known black holes lie thousands of light years from Earth, and even if humanity developed spacecraft capable of traveling that distance, the gravitational pull surrounding a black hole is so strong that no astronaut could ever hope to escape its influence. Light itself, the fastest thing in the universe, cannot break free once it crosses the event horizon. This boundary marks the point of no return, where physics, as we know it, breaks down, and where the very fabric of space stretches toward an unknowable singularity. Because no traveler could return to tell the tale, scientists have used the laws of physics, general relativity, and computer simulations to visualize what such a journey would look like. This week, NASA unveiled 2 stunning, hyper-realistic visualizations that aim to capture that experience as accurately as current science allows. These simulations do not rely on imagination alone. They are based on decades of astrophysical research, mathematical modeling, and an increasingly deep understanding of how black holes distort their environments. Jeremy Schnittman, an astrophysicist at NASA's Goddard Space Flight Center in Greenbelt, Maryland, produced the visualizations with the help of powerful supercomputers. He describes the project as an effort to explore 2 very different yet equally dramatic scenarios. In one, a virtual camera, representing a hypothetical astronaut or probe, approaches the black hole, skirts dangerously close to the event horizon, and then slingshots away, narrowly avoiding destruction. In the other scenario, the camera crosses the event horizon, committing to a one-way descent toward the singularity, where the laws of physics, as we understand them, can no longer predict what will happen next. This second journey ends in the unavoidable doom of whatever object or traveler crosses that fatal threshold. Humanity's knowledge of black holes has grown significantly since the first one was identified in 1964. Over the decades, astronomers have observed the effects of black holes on surrounding stars, detected the powerful jets they emit, and witnessed the gravitational waves produced by black hole collisions. In 2019, the Event Horizon Telescope collaboration released the first-ever photograph of a black hole's shadow, capturing the glowing ring of heated matter swirling around the supermassive black hole in the galaxy M87. Despite all these breakthroughs, black holes remain among the most mysterious objects in the universe. Their interiors are hidden from observation. Their gravitational fields twist light like a cosmic funhouse mirror, and their influence stretches across galaxies. This is why NASA's new visualizations are so fascinating. They allow viewers to witness in immersive detail what has always existed beyond the reach of direct observation. The simulations are available on NASA Goddard's YouTube channel and come in 2 versions. The first version provides a 1-minute, 360-degree perspective designed to let viewers look around, as if they were drifting through space themselves. With a virtual reality headset or even a mobile device, a person can move their viewpoint in any direction while the camera approaches the black hole. This creates a sensation of drifting toward an unimaginably dark and swirling abyss, watching as the star field twists, stretches, and warps due to the intense gravitational lensing. The second version is an extended narrated journey that explains the physics behind each visual phenomenon. As viewers watch space bend, light arc around the black hole, and time seem to distort, the narration walks them through why these effects occur and what they signify. The simulated black hole in NASA's visualization has a mass 4.3 million times greater than our Sun, matching the size of Sagittarius A*, the supermassive black hole at the center of the Milky Way. Sagittarius A* is a real astronomical object surrounded by swirling gas, stars orbiting at incredible speeds, and powerful gravitational forces. Scientists have inferred its presence by observing the orbits of nearby stars, which revolve around an invisible point with speeds and trajectories that only an extremely massive object could produce. NASA simulation doesn't attempt to depict the exact environment of Sagittarius A*, but it does mirror its mass, making the visual experience even more authentic. A black hole of this size would have an enormous event horizon, giving the viewer time to observe dramatic distortions of space and light before crossing the fatal boundary. One of the most striking effects viewers notice in the simulation is gravitational lensing. Because the black hole bends spacetime, light from stars behind it gets pulled around and warped into arcs, rings, and stretched streaks. As the camera moves closer, the entire star field appears to swirl, twist, and sometimes fragment into multiple images of the same star. This happens because the black hole's gravity forces light onto curved paths. To human eyes, this would look surreal, as though reality itself was melting or being stretched like taffy. As the camera descends further, time dilation becomes extreme. To an outside observer watching the astronaut fall in, the descent would appear to slow dramatically, taking longer and longer as the astronaut approached the event horizon. But for the astronaut themselves, time would feel normal, and the universe behind them would appear to speed up. Once the camera crosses the event horizon in the second simulation, the journey becomes even more extreme. No matter what angle the viewer looks toward, all paths lead inward. Space becomes so curved that escaping is impossible. The camera continues falling toward the singularity, a point of infinite density where all known physics breaks down. In reality, any physical object crossing this region would be torn apart by tidal forces long before reaching the singularity. These forces stretch matter vertically and compress it horizontally in a process known as spaghettification. NASA's visualization does not depict the gruesome destruction of the physical traveler. Instead, it focuses on the visual distortion of the universe as the fall accelerates. Stars behind the viewer would appear to blur into streaks, and the glow of the accretion disk outside the event horizon would fade into darkness as the pull becomes overwhelming. What makes these simulations especially important is that they bring the public closer to understanding one of the universe's most enigmatic phenomena. While scientists can study black holes through mathematical models and through the light emitted by matter swirling around them, the human mind struggles to grasp concepts like singularities, event horizons, and warp spacetime. By turning equations into immersive visuals, NASA allows anyone, even those with no background in astrophysics, to witness what until now has been confined to theory. These visual journeys ignite curiosity, spark imagination, and invite deeper appreciation for the strange and beautiful laws that govern our universe. For many viewers, the experience may be unsettling or awe-inspiring, but it offers a glimpse into a realm where the boundaries of reality itself begin to dissolve. Through these simulations, NASA bridges the gap between science fiction and scientific reality. While no human will ever return from inside a black hole to confirm their experience, we can now come as close as possible to understanding the ultimate cosmic mystery without endangering any astronauts. As technology advances and our understanding deepens, future simulations may reveal even richer details of what happens near and beyond an event horizon. For now, NASA's work stands as one of the most vivid, scientifically faithful, and mesmerizing windows into the universe's most powerful and mysterious objects.